Hi, and welcome to Quantum Computing 101. My name is Ian Lowe, and I will walk you through the basics of quantum computing. So, what is quantum computing? It is an area of computer science focused on the development of technologies based on the principles of quantum theory. Quantum computing uses the unique behaviors of quantum physics to solve problems that are too complex for classical computing. There are 6 things to note. 1. Everything is made of waves, also particles. 2. Quantum physics is discrete. 3. Quantum physics is probabilistic. 4. Quantum physics is non-local. 5. Quantum physics is, mostly, very small. 6. Quantum physics is not magic. Now let me highlight some differences between quantum computing versus classical computing. Quantum computers process information in a fundamentally different way to classical computers. Instead of relying on transistors, which can only represent either the 1 or the 0 of binary information at a single time, quantum computers use qubits, which can represent both 0 and 1 simultaneously. A quantum computer's power grows exponentially in relation to the number of qubits linked together. This differs from a conventional computer, which sees its power increase in direct proportion to the number of transistors. This is one reason why quantum computers could eventually handle some types of calculations much better than classical computers. While a classical computer has low error rates and can run in room temperature, a quantum computer has very high error rates and needs to operate in an ultra-cold environment. Let's talk a little on the history of quantum computing. In 1959, Richard Feynman noted that, as electronic components begin to reach microscopic scales, effects predicted by quantum mechanics occur. In 1968, Stephen Wiesner invents conjugate coding. In 1980, Paul Benioff describes the first quantum mechanical model of a computer. Yuri Manin briefly motivates the idea of quantum computing, and Tommaso Toffoli introduces the reversible Toffoli gate. In 1985, David Deutsch, of the University of Oxford, described the construction of quantum logic gates for a universal quantum computer. In 1994, Peter Shor, of AT&T, devised an algorithm to factor numbers with a quantum computer that would require as few as 6 qubits. Because of this work, the first United States government workshop on quantum computing is organized by NIST in Gaithersburg, Maryland. In 1998, Isaac Chuan, of the Los Alamos National Laboratory, Neil Gershenfeld, of the Massachusetts Institute of Technology, and Mark Cubanek, of the University of California at Berkeley created the first quantum computer, with 2 qubit, that could be loaded with data and output a solution. Now, before I get into quantum computing, let's talk a little on quantum mechanics. Firstly, I shall talk about the phenomenon of the wave-particle duality of light. This is to say, light can be seen as a wave, but also as a particle. Light exhibits certain behaviors that closely resembles a wave. For example, light reflects and refracts like a wave. Light undergoes interference. Light exhibits Doppler effect. But light also acts in another way. Photoelectric effect is the emission of electrons when electromagnetic radiation such as light hits a material. Electronics emitted in this matter are called photoelectron. The photons of a light beam have a characteristic energy, or photon energy, which is proportional to the frequency of the light. In the photoemission process, when an electron, within some material, absorbs the energy of a photon and acquires more energy than its binding energy, it is likely to be ejected. If the photon energy is too low, the electron is unable to escape the material. The gold-leaf electroscope experiment disagrees with classical electromagnetism, which predicts that continuous light waves transfer energy to electrons, which will then be emitted when they accumulate enough energy. An alteration in the intensity of light would theoretically change the kinetic energy of the emitted electrons, with sufficiently dim light resulting in a delayed emission. The experimental results instead show that electrons are dislodged only when the light exceeds a certain frequency, regardless of the light's intensity or duration of exposure. A low-frequency beam, at a high intensity, could not build up the energy required to produce photoelectrons, like it would have if the light's energy was coming from a continuous wave. Hence, Einstein proposed that the beam of light is not a wave propagating through space, but is made up of discrete energy packets called photons. Now let's talk about a very key concept of quantum mechanics: entanglement. Entanglement is a special close relationship between a pair of quantum particles whose fates are. Let me share a very simple example. Imagine you ordered 2 t-shirts, one in green and one in blue. The 2 shirts are delivered in identical boxes. You do not know which shirt is in which box. But once you open one box, when you see a green t-shirt, you will know that the other box will have the blue t-shirt. The green and blue t-shirts are entangled in a certain way. This is roughly the idea in which quantum entanglement is based. Let's talk about one of the most important aspects of quantum mechanics: superposition. This is the ability of a quantum system to be in multiple states at the same time until it is measured. The power of a quantum computer is based on this, where instead of having transistors that can only be 1 or 0 at a given time, a quantum computer can be 1 or 0 or both at the same time. This is the basis of the quantum bit, or qubit, which is the counterpart in quantum computing to the binary digit or bit of classical computing. Let's begin with a recap of classical computing. Classical computers uses bit to represent information that can be retrieved, stored, and manipulated. The classic bit is the most granular information in classic computing. It has either a value of 0 or 1. Other data structures is built upon the bit. At any moment in the execution of a classical algorithm, each bit is in a specific state, 0 or 1. This is one of its limitations. The size of the memory of a computer is commonly expressed as the number of bits accessible by the processor. It is one of the main contributors to the performance of a computer. Let us move to quantum computing. As mentioned earlier, the equivalent of a bit is a qubit. Similar to a bit, it can also hold the values of 0 and 1. Contrary to a bit, a qubit can also hold values that are combinations of 0 and 1. In this scenario, the qubit is in a superposition state. However, when a qubit is measured, it will return 0 or 1. Very roughly, it can be equated to the probability of a particular qubit when measured to return the value 0 or 1. I hope at this point, you would have some appreciation of quantum mechanics. In the following sessions, I will go into quantum computing proper and how it works. Thank you.